Any questions? Okay. I repeat, you can interrupt me anytime and ask questions, no problem at all. I am happy to be interrupted. In fact, having interruptions is most welcome. Okay. Okay, now let's so let's recall the basic definitions of group actions. I'll quickly recall what we did in lecture 2. Okay, so here is the definition of group actions, which G is a group and X is a set. And we write like this, which means G acts on X. What does it mean? It means there is a map from G cross X to X and satisfying the following axioms. I denote the image of the ordered pair G comma X just by Gx, write G next to X. Okay. You should remember that this is just the image of G comma X under this map. That is the meaning of this symbol. And what are the axioms? There are two of them. This is one of them, which looks like an associativity kind of thing. Okay, and second one is that identity of the group acts on X by just X. Okay. So of course, this is for all G, H in G, and for X, all X in X. These two axioms must hold. Just okay. We had also said what a G map between G sets is. So another equivalent terminology is that X is a G set. So to say X is a G set is the same thing as saying G acts on X. Okay, and what is a G map between G sets? So if X and Y are G sets and you have a map phi between them, then a G map between G sets is one that satisfies this property, that you have this. Okay, so sometimes you may write this as G of X, right? Because various different notations are used. You may write this sometimes G dot X or G circle X or G of X, right? So here I'm using dot, for example. So sometimes also written G dot X and G like this, like you write it as a superscript on the left. All these are various possible G of X like this, or even G of X like this. All these are different notations possible. None of them is wrong. You use an appropriate notation depending on the context. Okay, so this here I'm using dot here that just means G commutes, or phi commutes with the action of G. So whether I act G on X first and then take the image of phi, image under phi, I get the same thing as if I take the image under phi first of X and then act G on that. Now this action is happening in Y. This action is happening in X. Okay, that is understood. I don't have to use a different notation, right? using a different notation makes it cumbersome. So uh, it's good to abuse notation and use similar notation for different things uh, if they have the same kind of property. So if G and Y are G sets, and I will write Gx and Gy here to say that to denote the action of G on Y and the action of G on X. I mean, strictly speaking, this is a different action and this is a different action, but it would be rather, it will become very complicated if you start using different notation. We should be, uh, we should use notation sparingly. And sometimes, I mean, depending on the context, we should be aware of uh, if and disambiguate depending on the context rather than explicitly denoting it in notation. So what I'm saying is, so if two objects are different but similar, sometimes you may use the same notation to denote those. um, of course, in our minds we are thinking, although we are using the same notation, we know that they are different, and rather than explicitly denote this, build this into the notation, it is good to abuse notation and let the notation not disambiguate them. Use the same notation to denote two different things, but keep in mind, keep in the back of our minds that these two are different. That is nothing wrong. In fact, this we do all the time in mathematics. It's very important. Otherwise, we'll run out of symbols. We'll just be bogged down by notation. Okay. And in fact, abusing notation gives you ideas. So I encourage you to abuse notation, particularly in the theory of group actions. It's good to abuse notation. Okay. So this is what it means for this map to be a map of G sets. This is the axiom for the map of G sets. Okay, we had defined this, and we had defined orbits and stabilizers. Okay, so what are orbits? So we had introduced, so let me recall orbits. So introduce an equivalence relation on X, where, of course, I'm assuming there is a group G acting on the set X, or in other words, X is a G set. So what is this equivalence relation? Given X is related to, let's say X1 is related to X2, if there exists G in G such that Gx1 equals X2. This is the definition. Now, it was easy to see that this defines an equivalence relation on X. So if X1 is related to itself, because I can take G to be the identity, and if X1 is related to X2, like because of this, then I hit G inverse on both sides and see that G inverse X2 is equal to X1. I'm using the axioms here we had done this last time. And further, the transitivity holds. That is, if X1 is related to X2 and X2 is related to X3, then say H of X2 is X3, then to go from X1 to X3, you first hit G on X1 to go from G to X2, and then H on X2 to go from X2 to X3. So if I hit HG, the element HG on X1, I go from X1 to X3. Okay, so this is an equivalence relation. So I've talked through the proof that it's an equivalence relation. We did write down the formal proof last time in the lecture. And the equivalence classes, orbits, are by definition So this is the definition, are the equivalence classes under this relation. Under this equivalence relation. Okay. Now, what are stabilizers? So given x in X, given an element little x in capital X. So once again, throughout, G is a group acting on a set X. That's my notation. Given an X, an element of X, define set G sub X to be all those elements of the group G which, when I act on X, give me back this. On little x, give me back X. Okay. So this is a subgroup of G. So that's a statement which is easy to see. Okay, in some of the books, they may call it a theorem and write down a proof, right? It's important to understand the proof of this, but the understanding doesn't necessarily have to, does not, you don't have to necessarily write down formally the full proof to understand why this is a subgroup, right? It's often important to just go through the proof mentally. So let us do that. So why is this a subgroup? What all do I have to show? I have to show it's a non-empty set. It is closed under multiplication, and it's closed under taking inverses. Okay. So why is this a non-empty set? Well, identity is there because 1x is equal to x. So it has the identity element, surely. Therefore, it's a non-empty set of the group. Now, if given two elements, G and H, if Gx equals H and Hx equals X, then G times H will, because of the axioms that we have, you can rewrite it like this, but Hx is X if H belongs to this subgroup. So you can write this as Gx, but G also belongs to the subgroup, so Gx is X, so you write this. Okay, so Gh, if G and H belong to the subgroup, then G times H belongs to the subgroup. This equation proves that. Okay, and finally, if G x equals X, G inverse X also belongs to this group because I can hit this equation with G inverse on both sides. This side becomes the identity of X and 1x equals X. Here's the axiom here. And this side becomes G inverse of X. So G inverse of X is also equal to X, which means G inverse belongs to this G sub X, the stabilizer at X. This is called the stabilizer at X. Thus, we have proved that this is a subgroup. Okay, good. Now, the orbits and the stabilizer are intimately related. Yeah. And that is the key for many of the counting problems. Okay. So let me tell you the proposition, very important proposition. But before I come to the proposition, let me give you an example of a, so let me give you an example of a group action. Example of a group action. In fact, as I was telling you provocatively last time, it is the example of the most important group action. So let me put an exclamation here. Silence, please, Rama. So example of the most important group action. It's as follows. So you have a group G. G is a group, and H is a subgroup. Then G acts on this left coset space, G mod H. So let's recall what G mod H is. G mod H is the set of left cosets of H, which you can write G times H, where G is in G. Right? So this is the set of left cosets of H. So how does G act on this? Well, you do the obvious thing. So I want a map from G cross G by H to G by H, right? How do I do this? G, okay. Now let me take a element of the coset. So let's call it XH. And where do I send this to? I just send it to GXH, right? And how about the axioms? Well, axioms, what all do I have to check? I have to check that GH XH is the same thing as G acting on, right? And so this is the question mark. And 1 times XH is XH. Okay. These two are the, I have to check this. By question mark, when I write a question mark, it means I have to check these. Well, there's not much to check. So because what is this by definition? It is GH. So this thing is GH acting on X times H. So it is the left coset determined by this element. And what is this? This is the left coset determined by first you act Hx and then you G. So this is the left coset determined by this element of the group. But these two elements are the same. So they determine the same left coset. Okay, so this is all right. And this by definition is just 1 times X of H, which is just XH. Okay, so it's very easy to check these axioms. Okay, so, and why do I call it the most important group action? Because as you will see soon, every other action can be reduced to this action. Okay, we are coming to that. Okay, so okay, so here is the proposition. This is a very important proposition. So let me start writing this in a different font or different color. So you know it is important. So this is proposition. I had stated this towards the end of the last lecture. I'm going to state it again, and we are going to prove it now. Last time we didn't have time to prove it. I'm going to prove it now. And the proof is very simple. It's the importance of the proposition doesn't derive from the fact that its proof is difficult. So there are various different ways in which things are important. So sometimes the things are very simple. It's a very simple statement, but it has wide applicability, and you can derive rather surprising consequences from such a statement, from such a observation. For example, take the pigeonhole principle. So it's a very simple statement. There is nothing to prove. It's obvious, but there are many surprising applications of this. This is of a similar nature. There is nothing in the proof. It's trivial. You just have to look at it and say, "Oh, it's obvious." Okay, it's at that level. But then it's a very it is its use is what makes this very important. It's okay. Its applicability is what makes this important. Okay. So here is the statement. So let G act on X. G is a group and X is a set. G is acting on X. Let me remind you that at the moment we are not assuming any finiteness condition on G or X. G could be any kind of group. It could be a finite group. It could be an infinite group. X could be any kind of set. Infinite, finite, no condition on X. Okay. And let's fix X in X. Okay, an element X is fixed. This little x is an element of X. Okay. Let me now introduce this notation, G, and I'm writing X on the side here, right? Not sub. So that was here. This is not the stabilizer. This is something else. What is this? This is Gx G in G. So this is a subset of X. This is nothing but the orbit of X. Why so? Because what does the orbit consist of? It consists of all elements which are equivalent to X, right? Which means there exists an element G such that Gx equals Y, right? Well, those are precisely the elements that I'm writing here. I'm writing Gx as I vary over G. Okay. Many of these may give me the same element. I'm not saying different elements of G will give me necessarily different elements of, of X. They need not. For example, any element of any element of the group that belongs to the stabilizer of X will give me back X itself. Will give me back X itself. So different elements of G could lead to the same element Gx, but that's okay. I'm just considering the set of all elements that you obtain from acting various elements of G on X. Okay. So this is the orbit of X, and here is the proposition. Gx. So let us G by Gx. Okay, now this is a subgroup by our observation before. We are going to connect or use everything that we have said. So we have just checked that Gx is a subgroup, right? Now, therefore, this means the coset space, G by Gx, and G acts on this, right? Because we have said G, give me any subgroup of a group G, then G acts on G mod H by this action, this obvious action. So G acts on this. Okay. So we are claiming this is isomorphic to, there is a map from G by Gx to G times X, meaning, sorry. Yeah, you can say it's G times X, no problem. So that's the orbit of X. And this is a G map. Okay. Now, there are a few things to observe here. For me to be able to say that this is a G map, recall that we have just defined here. Where was that? Right here. G map between G sets we have defined here. So we are claiming now that there is a G map between this G set and this G set. Well, okay, let's observe. Let me change the font here, color here. So why is Gx, or let me say, observe that G, okay, observe that Gx is a G set. Okay, so let's observe that. So here is the observation. Let's make a more mm, uh, more general observation. Okay, now, so let me schematically show you. This is my X. I'm fond of writing this schematic picture. Okay, you should be aware of the pitfalls of using such a picture, but at least I find that I understand things better if I draw this picture. So I draw a picture like this. Okay, what this picture is supposed to represent is this set X, and each part here. So this is we are we have a this picture says that we have a partition of the set X. And what is that partition? That is precisely the parts of this partition are the orbits of X. Since they are equivalence classes, they are mutually disjoint. In other words, two parts, if they have a common, if they meet at all, they coincide. And if they otherwise, if they are distinct, then they do not meet at all. They have empty intersection. So this is a schematic picture of X with its orbits. Right. Now, okay, so here is a definition. So suppose I take a subset of X, let's call it X prime. Right. Can X prime be a G set? When can you think of X prime as a G set? I want the audience to answer this question. So because I'm afraid that I may be going too fast, or it may be getting a little too technical. So this is a good time to um, make sure that people are with me. So could somebody please answer that question? Suppose I take a subset of X and I want that to be a G set. In other words, I want an action on X prime. When do you expect such an action? Can somebody be unmute and answer that question, please? What
Restrict.
do you
Already we G act on X.
Yes.
So we restrict to X prime.
We restrict to X prime. Good. But X prime
Since
can
orbit
we
must be the sum of one orbit, equivalence classes.
Okay. That's that's correct. That's very good. So, but just to confirm, you seem to be on the right track. But just to confirm, can I restrict? Can you say that arbitrary subsets X prime will be G sets?
Yes, sir. Because G
So
X.
see, let's see. G acts on X, right? So
Yes.
G cross X to X, I have a map, right? Right. G X prime is a subset of X. Therefore, G cross X prime is a subset of G cross X. And therefore, given, let's say, X prime in X prime, G of X prime makes sense, right? Because I just think of this as an element of X and act on it. So does that mean I can think of any subset X prime of X as no? What is the property I want?
Arbitrary of X.
Let us not think like that for a minute, because what is the property I want? I want that G
X prime go X prime go to X prime.
Go, right. So you can think of this. So this is a G set means, okay. So let us make a definition here. Okay, sorry, I'll go to the next page and I'll come back here. Okay. So let's make the following definition. So let's call it Y is a subset of X, or let's say X prime. I started out with X prime. Okay. Is said to be, so once again, our notation is G is a group acting on a set X, right? That's our fixed notation. X prime is a subset of X is said to be G stable if, or sometimes, okay, sometimes it's also called G invariant. There are various terminology. You should be different books, different in the literature, various different terms are used. It's important to be aware of these and be clear on what it means in the given context. The same term may be used in two different senses in two different sources. So here G, we are defining this, or this term is also used if G x prime belongs to x prime whenever G is in, or for, okay, let me just write for G in G and x prime in x prime. So the thing is, if I take x prime, right, an element of x prime, and act G on it, there is no guarantee that that stays inside the subset, right? So I want this, if this is true, okay, if x prime is a G invariant subset of X or G stable subset of X, then G acts on X prime as well. Correct? I can take the same action, whatever action I have on X, and restrict it to X prime. So in order that I am able to restrict it correctly, I must have this property. Okay? Okay. Now the next question. Here is a question. Again, I want you to unmute and answer. What are the G stable subsets of X? What is your answer?
Orbits.
Okay, orbits. Okay, but are there other things other than orbits? So, for example, this is correct. Okay, so here is again. Let me draw that schematic picture. Okay, here are some orbits. So if I take, okay, let me here this color. If I take this orbit, for example, okay, the fact that I have drawn this picture means if I take an element here and let G act on it, any element of G, it will go to some place within that partition, right? No matter, I will not be able to go from this partition to this partition by acting any element of G. Okay, this is precisely that this condition holds for any orbit, indeed. So indeed, for orbits is an answer, but I want what are the G stable subsets of X. So I want all G stable. Can you think of anything other than orbits which satisfy this property? So let me give you a hint. Or should I give you a hint, or should I wait?
Union of orbit.
Very good. That's the correct answer. So for example, so in fact, here is the statement. So these are precisely, so I'll put that here. These are precisely unions of orbits. And take their union, that's also a G stable subset. So if I take two orbits or any number of orbits, doesn't matter, countable, uncountable, doesn't matter, any number of orbits and take their union, I still get a G stable subset. That's easy to see. Okay, so I am not proving this formally, but this is more or less obvious. If you are not convinced, you should write down a proof for yourself. And if you have difficulty with that, I'll be able to help you during the tutorial or later, even in another lecture. But for now, I hope this is at least intuitively clear. You should be, and if you don't feel the need for a formal proof, that is fine. If you do feel the need for a formal proof, then I invite you to write it down yourself. Okay, so these are precisely unions of orbits. Okay, very good. So If I have a G stable subset, then I can restrict the action to that G stable subset. Okay, that's the point. Okay, now let's get back to our statement of the proposition. Okay, so here I have an orbit. This is an orbit. So that's a G stable subset, right? Therefore, it is a G set in its own right. Okay, I repeat, it's a G set in its own right. It's a subset of X and it is G stable. Therefore, I can restrict the action of G to this Gx. This is the orbit of X. So there I get an action of G on this. So this is one orbit here, right here. If X belongs to this, X is here, then Gx is precisely this orbit. And I can restrict the action of G to that part of X. And this is Gx denotes precisely that orbit. Okay. Okay. So we have this as a G set, and there is just this is also a G set. And it makes sense to, now, given that these are G sets, it makes sense to talk about a G map between them. And what is the G map? It is the obvious one. So what is an element here? It is GGX. Okay, let me put this in a different color. So GGX. Okay. Where do you want to send this? Can somebody guess what it should go to? So this is a coset, right? GGX represents a coset here, and I'm waiting for the answer. One of you, I hope one of you can tell
G
me.
acts on X.
G acts on X, right? Very simple-minded. Just G acts on X. Okay. Okay. So note that G acting on X belongs to the orbit of X, right? So there is, I mean, the only thing I can think of, the only thing I have here other than X is, of course, G, right? And so the natural thing to do is let G act on X, okay? And that's what we are claiming. And this is a G map. And this is a map, first of all. This is a map of sets. And then this is a G map. Okay, let's see. Let's prove this. Okay, like I said, the proof is not difficult at all. It's a very easy proof. Okay, let's prove this. So the first thing in the proof is to make sure that this map is well defined. So let's call this phi, right? This is phi. Phi is well defined. So the problem in the definition here is, and this often happens in mathematics, when we define things on quotients. So this is a quotient, right? G mod Gx is a quotient. Quotient in the sense, it's not a quotient subgroup. Gx need not be normal. So this doesn't have the structure of a group necessarily. Nevertheless, you can apply the word quotient to this. This is a coset space. It's called a coset space. So G mod Gx is a coset space, but we have defined this image in terms of a representative G. So the problem here is that suppose GGX, so this is the well-definedness, GGX happens to be the same as G prime GX. Okay. If this is the case, then the images must be the same. Does this imply Gx equal to G prime X? This is what we have to check. This is what we have to check. Given this, we have to check this. Okay, let's see. What does GGX equal to G prime GX mean? Which means that this implies, okay, this is all fairly straightforward. Okay, all we have to do is just unwind the definitions and it comes out. Okay, so what does this mean? This means that G and G prime belong to the same. Okay, you can, for example, multiply by G inverse on this side and do this. But what it means is Okay, let me write it out. G inverse G, if you want to write one more step, Gx. If I multiply by G inverse on both sides, sorry, G inverse G prime here is Gx. If I multiply on this equation, both sides by G inverse, this side becomes Gx, and this side becomes G inverse G prime Gx. Okay? Okay. What does this mean? That this means G prime. So this is the subgroup itself. So this is to say that this coset equals the identity coset. This means G inverse G prime belongs to Gx. This implies G inverse G prime belongs to Gx. Okay, what does that mean? To say that it belongs to the isotropy means G inverse G prime of X equals X. That's what it means to say G inverse G prime belongs to G sub X, because here is my definition. This is the isotropy. Where is that? On further. Here, Gx, that's the definition. It's all those elements of G that fix X. So G inverse G prime belongs to the stabilizer precisely means G inverse G prime X equals X. Now hit this on both sides. Hit this equation on both sides by G. Act G on both sides of this equation. Okay? And that gives me this. So we have in fact proved this. Okay, so this implication, this series of implications proves this. Okay, okay. So this is a well-defined map. What all do we have to prove? Can you list? Can somebody please unmute and list all the things that we have to prove here? What else do we have to prove? The claim is that this is an isomorphism of G maps. Right? So what all do we have to prove? Right now we have just proved that it is well defined, therefore this is a map of sets. What all remains for us to prove this? Anybody? Please help me with some responses. Otherwise I feel lost because I don't know whether I'm making sense, whether I'm going too fast, too slow.
Bijection we want to prove.
You want to prove that it's a bijection.
Bijection.
So let's say it's injective and surjective. Okay, very good. Anything else we want to prove?
Homomorphism.
Or will that do it? Or okay,
Homomorphism.
that is a G map, right? This is a G map. Right?
Okay.
So you have to show that it's correct. You can use the word G homomorphism. Correct.
G
Let me
homomorphism.
also take this opportunity to say G maps are also called G homomorphisms. You are right. You intuitively use the word homomorphism, which is perfect. It's in fact valid. Yeah? G maps are also called G homomorphisms. There are other terms. They are called G equivariant maps. They are called intertwiners by physicists. There are many different. See, remember that we are studying the subject of symmetry, and symmetry is close to the hearts of many different kinds of people. So there are many different terms used for such maps: G maps, G homomorphisms, intertwiners, equivariant maps, etc., etc. Okay, so G map. Okay, these are the three things we have to check. Let's see. Is this map, which one is easy, do you think? Can you see the proof of anything? So there are three things remaining to be checked. Okay, let us just verify each of them. Which of these do you think is easy?
Injective.
Injective. How do you show it's injective? What do I have to show?
G is equal to G dot of X. Then in the well-defined, we take out the reverse.
Very good. Excellent. So this is what you have to show it's injective. Suppose I have GGX and G prime GX, and let's say these are two elements on the left side, And if they map to the same place, then there must be the same on this side. That's what injectivity means. So which means I want to prove this implication. So let me use a different color here. I want to prove this implication. That's injectivity, right? Because gx equals g prime x implies ggx is equal to g prime gx. How do I show that? Any idea? The answer is on the board.
You have to start n to.
So we have here. You start
means
here
like,
and get here. I'm giving you a hint, madam. So you start here, gx equals g prime x, and you want to end up here. Look, how did we go from here to here? We went along this. So if I want to come back, what do you do?
Take the reverse.
Take the reverse. Just observe that gx equals g prime x means this. All these actually are two-way implications. So this means this. That's the definition. This is nothing more, nothing less than this. And this means this, and this means this. That's it. So the proof of injectivity is just the reverse of the proof of the well-definedness. Is that clear? Let me pause there and ask if that is clear. I am claiming that we have proved injectivity.
Clear.
Clear? Very good.
Clear.
Yes, very good. Now, let's go to subjectivity. Is subjectivity clear? So what do I have to show? I have to take some arbitrary element in the orbit and show that there is some element here which maps to that. So let me start an arbitrary element in the orbit of x. What does it look like? It belongs to the orbit of x, which means it is of the form
gx, g.
It is of the form g times x for some g. And what element do I choose here? What coset do I choose here so that I get gx?
G.
And the answer is obvious. It's ggx. If I choose ggx, I'll get gx. That's by definition, right? So this is rather trivial, right? Easy. Should I repeat this or is this okay? Is this I'm claiming it is obvious.
Sure, it's clear.
Okay, very good. And finally, that it's a G map. So what do I have to show here? So to show that it's a G map, let me do it with a different color here, right here. So here I have this. So I apply it, an element H here and an element H here. And I want to see that if when I, okay, maybe that was not a great idea. Okay, so when I apply H here, take an element. So I have to say that this map respects the action. That's what it means to say that phi is a G map. Okay, look here. Here is our definition. Here. So instead of writing it out like this, let me say it in words. What it means is, if I take something on this side, let's not use G here because G is already taken. Let's say H. If I act H on X, and instead of G, I'm using an element H. It's just a matter of notation. So if I take HX and act phi, first act by H and then take the image under phi, that's the same thing as first taking the image and acting by H. So let us translate that here. What do we want? So if I take this, let me write it here on the side. This is what we are trying to do. Okay, let me use some other color, maybe here, green. I hope this will be visible. Okay, this looks good. So GGX maps to GX. That's what we have. Now let me map this to act H on this. If I act H on this, where does it go? It goes to HGGX. If I act H on this, it goes to HGX. H acting on GX. Like this. Now the question is, does this map under phi to this one? If it does, then we are done. That's what it means, right? It means that whenever I apply H, act H first and then go by phi, which is the same thing as first go by phi and then act, because this is also phi, and then act by H. So this action H, remember, happens, or action by H happens, this action, both these vertical lines are actions of H, but this action is happening on the left side and this action is happening on the right side. Okay. So is this true? Well, this is also obvious. Where does HGGX go? It's like this, but this is equal to, by definition, this is HG of GX. And by this definition, HG of GX maps to HG of X, but that's the same thing as this by the associativity condition. Okay. So this is also okay. Okay, you may complain that I'm not writing this very neatly. Okay, sorry for my board work. I could have been neater. It could have been better, my board work. But at the same time, I want to insist that many of these things are good to just write a few, rather than write full sentences, English sentences. It's good to think by just writing a few bits of notation and use that notation as an aid to thinking. What I often find is that people insist on writing full English sentences, and what happens with that is that you get lost in the language. You miss the argument. So it is good to think, not write necessarily full sentences when you are thinking. Of course, you should be able to translate this to a fully correctly written proof. But that we assume, that is one of the skills that we assume that every mathematician, working mathematician has. Okay, that's an important skill. But that is not the only skill. That is, as I have said before, perhaps an even more important skill, not perhaps, but surely a more important skill is to think correctly mathematically about these objects, not necessarily writing down fully formal proofs. Okay. Be that as it may, we have done the proof of this very important theorem. So we have said that these two sets are related by a G map, which is a bijection. And in particular, the corollary is that these two are, so we have corollary is, here's the corollary. So the hypothesis is G acts on X and X is in X. Okay, and then G, the cardinality of G by Gx is the same as the cardinality of the orbit of X. This is the statement. Like I was mentioning last time, this makes sense even when maybe things are not finite, but maybe if you want to be comfortable, just assume that G and X are finite. It's enough to assume X is finite, but you can, let's say G and X are finite. I repeat, this is not necessary to assume, but let us just concentrate on this case. Okay. So let me point out an application from the tutorial. So in the tutorial, we were trying to compute the number of elements that commute with a given permutation. So if you recall, there is this problem in tutorial sheet 1. So let me write it. Sigma is in the symmetry group Sn, and what we are asking for is the cardinality of the centralizer of sigma. Okay, let me write it. Z sigma is the centralizer. So it's all those elements tau in Sn which commute with sigma. Tau sigma is equal to sigma tau. Okay. Okay. Now, to solve this problem, you can proceed as follows. It's an application of this corollary, which we have just established. Okay. So think of G. So put G is equal to Sn. That is what we are putting, but let's think of more general group. Let G act on itself by conjugation. And I take, let me call X in G. So X is an element of X, but X is G here. So I use X as an element here when I think of the object being acted upon. G is both the person who's acting and the object which is being acted upon. So since this X I think of belonging to this G which is being acted upon. Okay, so X in G. So what is this? What is the action map here? G cross G to G. If I am given G and X here, can somebody please tell me what this action map is in the case of when it is conjugation action?
Gx G inverse.
Gx G inverse. Very good. Thank you. If I want to use this notation, I will use G like this as a superscript on X. That is a very convenient notation, but here is what it is, Gx G inverse. Okay. So I take this, and then if I want to apply this theorem or this corollary to this situation. So let us see what Gx is. What do you think Gx is, given in this situation?
Centralizer.
Yeah, it is those elements. So let's see. It is by definition those elements G in G. Now I write G because I am thinking of this is G as acting. So this G is here. Okay. Such that by definition Gx is equal to X. That's what the meaning of this stabilizer is. But that means, in other words, Gx G inverse, this is the same thing as writing Gx G inverse equals X. And that is the same thing as writing Gx equals Xg. So under this action, for this action, Gx is nothing but the centralizer of X. Okay. And what is the other side? So we have determined that this thing is the centralizer of X. What about the orbit? What is the other side? What about Gx? What does this consist of? This consists of all elements that I can get from X by acting various elements of G. But this is the action. So can you tell me what this is, please? This is Gx G inverse.
Conjugacy classes.
This is just the conjugacy class of X. So this is nothing but the conjugacy class of X. So the conclusion is that G by the centralizer of X, this is in any group and any X, G by the centralizer of X has the same cardinality as the conjugacy class of X. So in particular, I can apply it to a permutation. So Sn by, okay, before doing this, let me write it a different way. This is the index of the centralizer, right? This is called the index of the centralizer. So what we have is index. So let me write it in a different color because that's a theorem now, right? We have a result now. Index of the centralizer of X equals, or the number of elements. Okay, sorry, right? This is the index. Here I should write the cardinality of the conjugacy class of X. This is for any X in any group G. This is our result now. Okay, now let's apply this to the special case. Sigma is in Sn. So the index of the centralizer, which is Z n factorial divided by the cardinality of the centralizer of X, is equal to cardinality of the conjugacy class of sigma. Now, so what you get from this is that if you can do one of these, either the centralizer or the conjugacy class, if you can count the cardinality of any one of them, then you can compute the other, because if you know the cardinality of the group, which we know in this case Sn, it's n factorial. So if I know either the conjugacy class cardinality of that or the cardinality of the centralizer, then I can easily find the other. And what we had done in the tutorial was we had computed this. Not in general, but in some special cases. The tutorial, of course, listed this, the answer in general. Okay, we haven't done that yet, but we can finish that in the next tutorial. But the point is that there is this relation between the cardinality of the centralizer and the conjugacy class. And that is what we are applying here. If you apply that principle, then you can reduce the cardinality of the centralizer from knowing the conjugacy, knowing the cardinality of the conjugacy class. Okay. Any questions on this? Is it okay? Should I proceed?
Yes, sir.
Okay. Please go ahead. If you have questions, don't hesitate. So I want to point out another important corollary. So we all know Lagrange's theorem, right? What does Lagrange's theorem say? Cardinality of a subgroup. So if you have a subgroup of a finite group, then the cardinality of the subgroup divides the order of the group, right? Now, here is another important thing. Look at this. We have G by, let's use this, index of the cardinal, so it's a corollary of this corollary. So we have this. Okay, what is the index? Index is G by this, right? Centralizer of X equals, well, we can even go one more step here. Let me do this at this level. Okay, let me go back. It's simple. Let's do it at even at this level. So we have this Of course, we have been writing a cardinality of G by Gx, but now I'm writing this, which is the same. Because, I hope so then let's say G is finite group. If G is a finite group, I can write this, and G is acting on X, and X is in any element of X. So you have this. What you observe is that this thing is a divisor of G. This divides G. Right? Because when I multiply it by the cardinality of Gx, I get cardinality of G. So here is the conclusion. The cardinality of any orbit of G divides the order of G. So the cardinality of any orbit of G divides G. In particular, look at this. Conjugacy classes are orbits for the conjugacy action. Any orbit of G under any action. Let me also emphasize that. Under any action. We have not used anything about the action. Under any action. That is the important part. So if I apply it to this specific action, I get, so in particular, so let me go back to pink here. In particular, the conjugacy, the cardinality of any conjugacy class divides the order of G. Okay, that's the conclusion we can get from this. Okay, let me pause here again and then ask you if you have any questions. Is this okay? Is it clear? I'm waiting for some response.
Clear, sir.
Clear, okay. Let's do an example. So I'll go here. Right, okay. So this is from the tutorial sheet 2. Let's do an example. It's maybe good to do an example. So Sn acts on 1 through n, right? This is the defining action. Okay, so I take the element n, say. So this is my G, and this is my X. I take the element n in X. Please tell me what the stabilizer of X is and what the orbit of X is. Just let's compute these two just to be sure that we understand. And what is the cardinality of G itself? That we know is n factorial. It's the symmetric group. Okay. So please tell me this.
Orbit of X.
Orbit of X is?
1, 2, 3, etc. n.
The whole thing. The
whole
orbit
thing.
is the whole thing, right? Okay,
Yes,
very good. This is the whole thing. 1, 2, 3 up to n. And why so, madam? Could you explain? That's correct. Correct. The answer is correct. Could you just explain?
Identity. Okay, sir. G, that is sigma belongs to Sn. Suppose sigma is an identity, then take X is equal to 1, 1 goes to 1. Suppose I take sigma equal to 1 goes to 2, then sigma of 1 equal to 2. So similarly, it will go on.
Correct. So here we are talking about the orbit of n, right? This is my X. Correct. But the same argument applies to the same argument applies to n as well. So there is a permutation. You can send n to anything you want. Meaning, as I vary over all permutations, n can be sent to anything that you want. Correct? So for example, if I want to send n to 2, there are many permutations which do this, right? I can, for example, take the cycle 2, n, right? What does it do? It sends n to 2, 2 to n, and fixes the others. This is not the only permutation that does it. There are many different ones that do it, but this is one of them, right? So instead of 2, if I choose 3, I can take 3, n, that sends n to 3, right? So as I vary over all permutations, I see where n moves, right? The word orbit is very graphic. I mean, it has graphic connotation. So you should use this. You should think of n moving under various actions. So you should think of G as some machine which pushes n around, and see where all it goes under the action of as it gets pushed around by various elements of G. And it is clear that indeed you can push it to any element whatsoever, and indeed that is every element belongs to the orbit. It's a single orbit. Okay. How about the stabilizer of n? What is that?
N minus 1 factorial.
Correct. The cardinality is n minus 1 factorial, but can you identify the group? That's correct. The cardinality of Gx is n minus 1 factorial.
X. Fixed X. So collections of permutation, fixed X.
Which fix x, but in terms of now x is n, therefore it fixes n.
N.
Can you? Yes, correct. That's from the definition. It's all those permutations which fix n. But can you give a slightly different description of it? That's correct.
Symmetric group is n minus 1.
Correct. Very good. That's what I was expecting. This is nothing but Sn minus 1 sitting inside Sn. This is the subgroup which fixes n, right? Of course, that when I say that, I'm just, it's a tautology. I'm just repeating it. G sub x is the subgroup which fixes x. Therefore, this is a subgroup of Sn fixing n. You can think of this as permutations of the first n minus 1 elements. Okay. So here we have this, we have to verify this. So the index here, let's just verify this. We have this equality. Let's see if this is valid. Here, instead of G, cardinality of G, I substitute n factorial. Gx is n minus 1 factorial. It's this symmetric group. So the description of this as this symmetric group helps me compute its cardinality. If I just say it's the subgroup that fixes n, that is just the definition. But I can think of it as the symmetric group Sn minus 1. That is what helps me compute its cardinality, right? And this is equal to, this is n. So indeed, that is correct. So this is a very simple example in which we have checked that we have computed the stabilizer, we have computed the orbit, and checked that this equation holds, right? The index of the stabilizer equals the cardinality of the orbit. Okay, very good. But this fact is a very important fact. Often elementary books on group theory don't have this very important fact stated. In the cardinality of any conjugacy class divides the order of G. This is a very important fact. So I want to emphasize this. And if you haven't seen that before, then that is something you can take away from this lecture. Okay. Okay, so we are running out of time. So maybe I'll stop. I can stop here and ask for questions rather than go ahead. So I said that we will prove Burnside's lemma and we will apply it to the necklace problem. Well, I underestimated the amount of time required. So I have not been able to do it, but that's no big deal. We can do it next time. If I'm going too slow, you should tell me now so I can go a little faster and cover more material. But I don't want to cover more material at the expense of losing people. So please advise me whether this is too slow or too fast. I need some feedback to calibrate the speed of the next 3 lectures. Okay. Uh, the floor is open to questions. Please unmute and ask questions if any. So let me ask, had you seen this before? Is all this familiar to you already?
Sir?
Yes.
Yes, sir. We studied in group theory,
Yes, sir.
normal subgroups, fundamental theorem of homomorphism, some related things. In group theory, we had studied, sir. Fundamental theorem of homomorphism,
Right.
normal subgroups, and then
Yeah.
the GX, G inverse, it all represents actually the normal subgroup, and then cosets. That action GX, it actually represents the cosets. And then Lagrange's theorem, that order of H divides order of G.
Yeah, order of the subgroup divides the order of the
And
group.
order of
Yes.
the subgroup divides order of G likewise.
Yeah. So, okay, by that you mean these things you hadn't seen. So this
Yes,
is
sir.
new to you.
This is a new thing.
This
for
is
us.
new thing. Okay, good.
New thing.
I hope you. I hope the new thing was understandable, and I hope you like it. And so that's good. If it is new, then it's useful, I suppose. You are learning something new, which is one of the points of this TEW.
Yes, sir. Yes.
Okay. Any other comments, please? I need to know. Let me ask you, madam, is this too fast? Am I going too slow?
Sir,
Yes.
sir, we are safe in this speed, sir.
Sorry.
We understand the concepts that you explain is very well, sir. Please maintain the same speed, sir.
Okay. Okay. Thank you for that feedback. That's very important for me. I was not sure whether I was going too slow or too fast. Now you're saying, of course, for some people it may be too fast, for some people it may be too slow. We are all different. Maybe for people who have seen this, it's too slow. People who have not seen this, it's too fast, etc. But we will take an average. We will do an average of all the opinions. So thank you for your opinion, madam. I understand that you want
Sir,
me to maintain the same speed.
From algebra, sir. We stopped study at MSc level, sir. We did research at another field. So
understood. You have maybe studied it in MSc, maybe, but now that you are thinking you don't use algebra or you don't teach algebra, these
yes,
things are not.
I don't teach algebra, sir. That's why the speed is very comfortable for me.
Very good. Thank you, madam. Thank you, madam.
Sir.
Yeah, thank you. Thank you for that feedback. I appreciate it. Is there anybody who thinks this is too slow? Please be frank. No, I won't get offended if you say this is too slow or that it is too fast. Maybe I'll stop sharing and if some of you would, let's see some faces. I don't mind seeing some faces. So if you can switch on your videos, it will be nice. Yeah. Thank you, madam. So just to get some personal feedback. Good to see faces. Is there anybody who thinks this is too slow?
No, sir. It's the correct level, I think. So.
Correct level. Okay. Thank you, ma'am. Anybody who thinks this is too fast? Okay. I guess nobody's saying. So I assume this is about the right pace. So I'll try to maintain this pace. we don't have to, it's not like we are rushing to find, finish some syllabus. So we will cover whatever we can. Okay, we will neither we'll neither go too slowly nor too fast. We'll go at a comfortable speed and see what we can cover. Okay, and there are things in the chat. Oh, need fast. So Annamalai is saying is that, what does yes? Okay, it's clear. Yes, let's see. Somebody is saying I should be going faster. May I ask who that opinion is from?
From Annamalai, sir.
Okay, so here is the solution. See, if I go very faster than what I'm going, it's very likely that I'll lose people from the other reactions that I have so far obtained, and the reactions that have been expressed. It looks like if we go faster than what the pace we are going, then we will start to lose people. So I will not, unless there are lots of people who suggest that I go faster, I will resist the temptation to go faster and maintain this same speed. Okay. Having said that, let me offer some compromise for those who want me to go faster. It's comfortable for those who are not working in algebra. That is the comment. Okay, good. Thank you. So we will go at this same pace. For those who want me to go faster, I suggest you read the notes, and there are many questions there. Okay, there are questions in the tutorial sheet which are of the harder kind, and you can try those. And there are questions in the notes that I have distributed. And of course, there are many other sources from which you can get various questions. So for those for whom this material is not new, who have seen this before perhaps, or for any reason this feels too slow, you're welcome to do the harder problems, and we can discuss some of those during the lecture, and I'll be happy to drop hints. I can try to address some issues, very quickly for those who want to go faster. Okay, so here is what I'm saying. We will maintain the same speed. So it is people who are not working in algebra can also follow. We will do that. But for those who want me to go faster, for those who want to see more material, what we will do is I'm suggesting that you look at the tutorial sheets, the harder problems, or come up with some problems yourself, and we can discuss some of those very quickly in the lectures or tutorials. Those portions, not everybody may follow, but that's okay. That's okay. It's some of this may go overhead for some people, but the main course will be at the same pace. Okay, I think with that, if there are more questions, specific questions, I'm willing to answer, but we'll meet tomorrow then. Otherwise.
Yes, sir. Tomorrow we'll see.
Okay, 1 o'clock, Professor Anirban will be here, tutorial.
Yes, sir.
And I'll be
5 to
assisting
6.
him. 5 o'clock, we'll have my tutorial with Professor Anirban assisting me. Okay?
Yes. Okay, sir.
Okay, thank you. However, if there are more questions, I'll be around for a few minutes, so you can ask.